Okay, well, due to my total lack of success getting CANbus working on my circuit board, I thought I would check to see with the company that actually made the chip and made the software tools to see if they can make things work, because they know what's going on. They're actually electrical engineers and electronics technicians, and they can walk across the street and talk to the guy who designed the part or wrote the software. Let's see what's inside. And here we have it. The SAM C21 Xplained Pro Evaluation Kit. So this is a board designed and built by Atmel, now Microchip, and ordered and sent to me from RS Components in just a few days. I really like this company. They've got what I need, and it's here fast. I'm not sure where their warehouse is. They have a website that's Thailand linked. I don't know if they have a warehouse here or it's coming from Singapore or where it's coming from, but they do the job. These Xplained boards are hardware prototyping boards that look a lot like an Arduino. It has all the pins all the way around. It's not an Arduino footprint, but it certainly gives you access to all of the functionality of the chip. And this SAM C21 is my microcontroller family, but the board uses the J version of the chip, and I'm using the C version of the chip. The J is a physically larger package with more pins and more internal function is exposed to the world, where mine's a smaller chip with fewer functions exposed. In checking the spec sheets, it looks like the only significant difference is this has 2 CAN channels and my board only has 1. So it should be electrically compatible and software compatible too. So let's open it up and see how she looks. And here she is. You can see a tremendous number of input-output pins and different headers. And on the bottom it's got little rubber feet, which is nice, so you can actually lay it down and it stays in place. It does look like an Arduino style footprint, but it's definitely not. From what I can see on the silk screen, the pinouts are not compatible, so it's not going to take an Arduino shield. But yeah, this one. So this is the J version of the chip. I think it's 64 pins, or maybe 48. Yeah, 48 pins I think, and mine is 32 pins. Across the top, I believe this is a current sensing jumper. If you want to measure current of what you're doing, you take the jumper off and you put an ammeter in there. This is a software accessible push button that you can read in your software. Reset button. It can be driven by 5 volts or 3.3 volts. Your USB separate power input. This is the debug header, which goes with the Atmel debug board. It's got a row of output pins, and these are male, female input-output pins. This is I2C bus right here. We've got ground, we've got digital ins and outs. Across the bottom on this side, we've got analog ins and outs, and reference voltages and power and ground. LIN bus, CANbus, this is what I'm interested in. And here we have an external crystal. I don't have a crystal on my board because the chip itself has I believe a 48 megahertz internal crystal, although I don't know about the accuracy of that. Here's the digital to analog converter output. You can solder in another crystal here if you want. And this is MISO and MOSI bus for chaining to other devices. So it's pretty well equipped. And there's the back side. I think these might be opto-isolators and another Atmel chip. I'm not sure what that's driving. I'll have to look up that part number. The other good thing is the Atmel tool system knows about this board. And when you plug it in, it automatically says, oh, you're using our C21 Xplained board, here's a bunch of samples that you can use. Sample device config and sample code. So let's see if we can make this guy talk. Okay, we're sitting here. I've got the debugger plugged into the Xplained board, and my little board is sitting over here, unpowered on. Don't worry, little guy. You're fine. We'll get back to you later. And I also have Atmel Studio running here, no project open. So the first thing we do is we plug power into the debugger, and it's power and communications at the same time. Windows recognizes it. Still no change. Then I plug USB power and communications into the start board. And look at that. It opened up a tab. And there's our board. It knows from the device signature that we have just plugged in a C21 Xplained board, which is pretty cool. And it's given us some things to click on. So let me jump over to screen capture and we'll start clicking on things. Okay, here we are in Atmel Studio, and we've got a few things to click on. The first one is New ASF Example Project. And if I click on that, it takes us to this pop-up box, which is loading all the possible projects that they've provided for this board. And if I select in the list SAM C21, it says we've got 91 possible sample projects that we can learn from. Now, the downside is it says this version number 3.4.0. This is ASF version 3, which is not ASF version 4 that I've been using, because version 4 is simply not an improved version of ASF 3. It's totally different. I mean, totally different. So this helps me in no way, other than giving me some pre-written samples written to a different framework that I cannot use in my application. But let's go ahead and see what they provide and see if there's any value here at all. We've got clocks, we've got quick starts for the comparator, analog to digital converter, callback, that's something I've tried to use in version 4, CANdriver. This is going to be especially helpful for me. We've got digital to analog converters, we've got EEPROM, events, real-time clock. The J version of the chip that's on this board has a real-time clock inside, which I do not have in my C chip. Real-time clock knows what today is, it knows dates, it knows calendars. All the C chip knows is the number of microseconds since it was powered up. Serial communications over I2C and SPI buses and USART. This callback would be particularly helpful to me. We've got all these other drivers and a bunch of unit tests, which is good. Programmers tend to not like to write tests, so that's nice. Let's go and explore up here, the CANdriver, and see how it looks. Okay, we are now in the sample, and you can see over here, this is a totally different directory structure and file naming convention than ASF4. This QS CANbasic, Quick Start CANbasic, is the main for this program, and it's got a few header files that get created along with it. So let's take a look and see how this sample works out. They're claiming copyright all the way up to 2018 for an old version of their software framework, which is puzzling. Why are they supporting 3 and 4 at the same time? Anyway, so we've got a bunch of defines with these magic numbers, filter IDs. These have to do with the CANbus IDs that we'll see later. We've got data buffers. We've got other variables for the whole module, configuring the USART port. Configure CAN. So what do? We come through here and we initialize some buffers. and we set up the transmit and receive pins using this pin config structure, mux position, and some defined magic numbers that go in here. So basically it says these are the pins I'm going to use for my transmit and receive. We initialize the underlying driver with this CANconfig structure. It's all magic. We initialize it and we start it, and we enable interrupts to happen, error arbitration and error data. We set up a filter to only filter the messages that we want to look at for this sample. There's a 0 filter and a 1 filter, an extended 0 and an extended 1. Here's a method to send a standard message with the ID and the data and its length. It sets up some things in a buffer and does some tremendously magic bit fiddling into this register. Sets the data length, again magic things getting set into a register, which is pretty much how version 3 works. It's all setting magic numbers into registers because this software layer was written by hardware engineers. They didn't try to abstract a usable software layer from an underlying hardware representation of how the chip actually works. So now let's look into the handler for incoming CAN messages. Okay, so this method gets called when a message is read on the CANbus that passes the filtering of IDs that's already been set up. So this indicates a message we're interested in has been received. We check to see if it's a new message in the receive buffer. Then we scan through, we clear the status, we look through a bunch of different buffers to check their status. We clear it, we receive elements out of buffers, we check bits to see if it was an extended or a standard message. We copy in the data from the buffer according to some other flag, and that's it. But that's for a new message in the buffer. This is for a new message in FIFO 0, a new message in FIFO 1, or an error. Great. So we've got 3 different things that can possibly happen when we receive a new message. Here's where they display the menu to the user, where you can set filters, you can send a standard message, you can set filters, you can send an extended message. So that's good. These are all the kinds of things you want to do when you're testing CANbus. And at the end, here's the main. We initialize the system, configure the USART, configure the CAN, display the menu, and then go through here and check to see what the user typed in and what they want to do. But before we run this code, there's a very important thing we need to know, and that is what data rate are we actually going to be reading and writing from on the CANbus? Because it's just like serial ports. You can specify the baud rate essentially of your CANbus, and you do that, and we can go over and click on this conf can header file, and this specifies our FIFOs, some buffer sizes, some other buffer sizes. Here's the critical part. Now, in CANbus, you don't just simply say, here's the baud rate I want. There are 4 magic numbers that go into defining the resulting baud rate based on a number of factors. Now, you start with the clock frequency of your microcontroller, and in the case of the C21 family, it's 48 megahertz. This J chip's running at 48 megahertz, my C chip's running at 48 megahertz because of an onboard oscillator. Great, so I can assume these numbers also translate directly to the way I want my board to run. Now, how do we get from 48 megahertz down to a 500 kilohertz baud rate that we want our CANbus to run at? The first thing we do is we have this thing called the baud rate prescaler, which takes your 48 megahertz and divides it way down. So you take this 5 number right here and you magically add 1 to it, which is 6. You divide that into 48 megahertz. That gives us an 8 megahertz effective clock rate that we're now dealing with. Now, this is where things get weird. We then take that 8 megahertz and we divide it by another set of magic numbers, which gives us our resulting 500 kilohertz. This is derived from magic number 1 plus the before number plus a 1 plus the after number plus another 1. And that's this 10 and 3. Depending on the underlying CANbus. Now, CANbus is designed to work in very noisy electrical environments and be very, very tolerant of non-squeaky clean signals coming through. So basically, this is a system that allows you to select what kind of tolerance you have for where your bit is going to change from a 0 to a 1, or the next bit that's expected along the line. And it defines these different magic things that happen, and you're allowed to, with a very high degree of selectivity, set how you want the hardware to be detecting these things. And I'm going to jump over to this calculator that's provided by CANbus, which is one of the companies at the forefront of CANbus tooling in the world. They have some incredibly expensive tools to work with your CANbus devices. So we're going to use their calculator. I'm starting with 48 megahertz. I want 500 kilobits per second, and it allows me to select my tolerance. So let's be the most tolerant that we can, and we're going to calculate a new table, and here are the numbers. Now you can see, given 2 input numbers, it's giving me this giant table of possible values. And if we scroll down, we can see here's a section with the 5 divider and a 3, but they're giving an 8 and a 1, giving us our 500 kilohertz output. But the Atmel folks in the tool, they've decided to go with 3, 10, and 3, giving 500 kilohertz. And that's okay. There's too much black magic here. I'm going to stick with 3, 10, 3. And there's also something called nominal and data, and they've set them both to 5, 3, 10, 3. So who am I to try and second guess the people who designed the chip? So this is what I'm going to go for. Okay, I've got my digital oscilloscope running, and it's trying to decode and capture CAN data. Come over here. We'll run the code and we'll see the menu that comes up because I've got my serial port connected in software. And there's our menu. So all I want to do is something simple. We're going to send a standard message with the ID of 45A, and we're going to send 4 data bytes along with it, 0, 1, 2, and 3. So I come down here and I hit 2, and let's see what happens. Oh, it's freaking out. Protocol error. Please double check the clock in 2 boards. And over here, oh, I have to restart. We're not really getting a good CANbus signal. It's trying. There's stuff coming out on the bus, but it's not decoding anything, either symbolically or down here in the list. And this is what I was getting with my board. But it's really interesting that we're getting a bajillion error messages here. Protocol error, please double check the clock in 2 boards. Maybe my problem is yet another naive assumption I made, that I could just hook up my scope to the board and put out a message, and the message would be seen and decoded, and Bob's your uncle. Maybe I've got to connect 2 boards together and have a actual working CANbus system for it to successfully send and decode messages on that wire. I figured it would work like a power supply. You turn your power supply on to 12 volts and you can measure 12 volts on it. Okay, so let me go in. I'm going to set up the firmware in my board to 5.3.10.3 in my settings to try and get 500 kilohertz on the bus, and we'll see what happens. The way we change these 4 magic values in ASF4 is we go into Atmel Start, select the CAN device, and go down to its settings pages, and here it is, the normal and data, bit timing, and prescaler. So you can see it comes predefined with some other magic numbers, and all you have to do is go in here and say my prescaler is 5. Now what I did here is a rare occurrence. I have found that Atmel Start will not let you type a new number in here. So what I've had to do is exit in and out of Atmel 3 or 4 times before it actually lets me edit this field. At first I thought it was uneditable and I was going into hack header files, and then I realized no, it's just another bug. So prescaler time segment before is 10, and it gives that delay where you think everything's failing. Time after is 3, and the resync jump is 3. We're going to do the same thing for data. 5, 10, after and resync jump are both 3. I'm going to leave everything else the way it came from the factory. I hope that's right, but we'll only find out from more testing. So I'm going to save and generate the project. Then I will flash it onto the board, hook up the 2 CANbus wires between the boards, and we'll see what happens. Okay, my board has been flashed with the 4 magic numbers for its bit rate. The 2 boards are connected by these 2 wires, CANbus high, CANbus low. My meter probe is on CAN high. The Xplained board is run the sample, and we're at its menu prompt right here. So all I want to do is send a standard message right here. So we're going to do command number 2, and I hit enter. Protocol error again. What's our, let's see. We're getting some transmission on the wire, but it's not able to decode anything. That's a tremendous amount of ring on the end of the signal. Now, CANbus is supposed to have a 120 ohm resistor on each end of the bus. I do not have that on my board. I don't even have an option for the user to select that. I suppose that'd be good for the next version. The Xplained board, I don't know if it's got a 120 ohm terminating resistor there or not. Let's try something else. Okay, I added a 120 ohm resistor across my CAN high and CAN low, and yes, the board does have it. It's actually in the form of 2 62 ohm resistors that are bridged across there, with the common point as a cap to ground. I've never seen that in any other documentation. But let's see what happens when we go command 2 and contact. Still have our protocol error. Let's see what the scope says. We still have a lot of ringing on the signals, but it's not decoding anything on the bus. But we have a minor success. With all the garbage that was going through, I actually spotted one good packet, and it's right here. I stopped the capture, and I'm looking at buffer number 10, and it highlights this. And I was doing another test with an extended packet. The ID is 45A, and it's sending 4 data bytes containing 0, 1, 2, and 3. And that's it right here. ID 45A, data 0, 1, 2, 3. good cyclic redundancy check, which is a kind of parity checking. Bit stuffing is valid, but the packet itself is not valid. I don't understand. All this stuff seems to be okay. And I come up here and I highlight the packet and it says everything's good. I can't move the pointer to show you, but look at that valid-X. So everything looks okay except it's not valid, and I'm getting a lot of gibberish, and then every now and then we get one good packet. Meanwhile, the tool is flaming over here saying protocol error, but I actually did manage to catch one good packet, and I don't know why. I got one and a bunch of bad ones, and yet the whole packet is marked not valid. So we're getting close. As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.